So I will talk about the conjectural symmetric version of the Ehrhard inequality. I put a link in the chat for the Scribble where you can see the slides. There is a lot of information on the slides, but hopefully I'll try not to go too fast, and I might just not tell all of it, but you can see it written. So I will denote the Lebesgue measure by, as written here. The Gaussian measure I will denote as letter gamma, Minkowski sum of sets. There's a standard notation for the Minkowski sum. The CDF of the Gaussian measure is written here. And note, by the way, that the inverse of the CDF of the Gaussian measure has the property that if I consider a half space H, let's say, and the Gaussian measure of that half space is equal to A for a fixed number A between 0 and 1, then the point on the x-axis where the half space intersects it is precisely phi inverse of A. Okay, so this is the notation. Let me remind you about Lebesgue isoparametric inequality. It's something that's like very classical. It follows as one of the probably best proofs of that is by the Minkowski inequality written here at the top that we learned about also in the Rand's talk earlier. So this is the Minkowski inequality. It tells us that the volume is concave, 1 over n concave in the Minkowski addition. And the isoparametric inequality tells us that whenever we have a Borel measurable set of fixed Lebesgue measure, the perimeter is going to be smaller for the ball of the same measure. So the perimeter of K is bigger than the perimeter of the ball of the same measure as K. And note, by the way, again, here the ball of the same measure as K has radius A to the power 1 over n, if A is the measure. That's supposed to be reasonably straightforward. So here is a very short proof, right? We just write the definition of the perimeter. This is the definition of the perimeter. We apply the Minkowski inequality and do the algebra. Discover that the ratio of the perimeter raised to appropriate power to the scaling and K is going to be bigger than that of a ball. The rest is just out. Okay, so there is an analog of all that story in the case of the Gaussian measure. So I remind you, the Gaussian measure is a measure with the density e to the power minus x squared over 2 with the normalizing constant. And there is a very nice inequality called the Ehrhard inequality. The general case of that inequality was proved by Borel that says that if I apply the function phi inverse to the Gaussian measure of the average of sets, then it's also concave. Again, function phi is a Gaussian CDF, and phi inverse is you can think of it as the x coordinate of the half space whose measure is A. And the Gaussian isoparametric inequality that was proved originally by Sudakov and Serison and Borel. So it says that among all the sets of fixed Gaussian measures, the half spaces have the smallest Gaussian perimeter. And you see again, here's some similarity. Here we have a ball of radius A to the power 1 over n. Here we have half space meeting the x-axis with the value phi inverse of A, and phi inverse is a function involved in the Ehrhard inequality, and t to the power 1 over n is a function involved in Minkowski. Here is a proof of the Gaussian isoperimetry from Ehrhard. And it's just a little bit more involving than the proof of Minkowski because we don't have homogeneity and slightly less nice, but here it is. It's just written down. Again, this is the definition of the Gaussian perimeter, and this is the application of the Ehrhard inequality. And here we have to introduce additional parameter and bypass the homogeneity issue. And like I said, the rest is out. So this whole project, it builds on some ideas of variational methods, which is very appropriate for this conference. So I just put a slide here in order to kind of have general idea. I'm not going to return much to this sort of proofs, unfortunately, but I also wanted to put some names here. So But the idea is like this: we take a set, for example, convex set, or convex, usually typically convex set. We take and we perturb it a little bit by perturbing its support function, or you can call it any other name you want. We perturb the set a little bit, and the Minkowski inequality tells us that if our perturbation goes along the Minkowski interpolation, if the perturbed set is the Minkowski average of our set and some other set, then the perturbation, the volume is 1 over n concave. In the Gaussian case, it's phi inverse concave. And in general, if you have some function that satisfies this inequality as written on the second bullet point here, then it's concave in T as this one-dimensional function. Therefore, second derivative is 0. Second derivative we take, and so basically this means that the function satisfies the following inequality: f double prime of a divided f prime of a is smaller than something that depends only on the set and on our perturbation here. M is a measure of the set perturbed. All this method was developed actually in a huge amount of papers, but particularly in the context of the Minkowski inequalities, these are some notable papers that are written here. Colasanti used this idea to deduce Poincare type inequality on the boundary of convex set from the Minkowski inequality. Kolesnikov-Milman actually managed to prove the Minkowski inequality using this local form, which is quite remarkable. And they also followed up with a number of other results. I will talk about my papers on the subject actually on another slide once again. I will not sharpen attention to that. Let me now finally come to the sort of main question of the talk. Actually, first I will mention a different question and then the main question of the talk. So here is this so-called Barth-O'Donnell problem, conjecture posed forward by Heilman, attributed in his paper to Frank Morgan. So honestly, I don't know what name to attach to this problem, but here's the question. Suppose we have a measurable symmetric set in rank. It's symmetric with respect to the origin. Suppose its Gaussian measure is fixed, it's A. Then the perimeters in the conjecture says that the perimeter, sorry, I made a typo here, of the set K is bigger than that of a set CA, which is a round K cylinder of Gaussian measure A, or its complement. Gaussian, what do I mean by round K cylinder here and throughout the talk? It's a set of the form RB to K times Rn minus K. So it's a ball of some small dimension or full dimension times the space of the remaining dimension. So strip, ball, cylinder are all round K cylinders. So, and in this case, of fixed measure A. So it's conjectured that those guys are isoperimetric minimizers for the Gaussian surface area among symmetric sets. So Heilman has worked on this question and proved it under some additional assumptions. Pachesi and Julien verified it in the case of symmetric strips for very large A. So if A is very large, this the best round cylinder in this case is going to become a strip, as one can check. And so in this regime that's very close to 1, Pachesi and Julien proved it. And outside of that, as far as I know, not much is known on the question. Let me discuss a seemingly, maybe only seemingly related question. What is the optimal function or an optimal function such that for all symmetric and convex sets KNL, we have this inequality as written here. So notice there is a slight difference. I only permit here convex sets. So for instance, I don't want to look at their complements. I talk about symmetric convex sets. So the question is, what is sort of the best fun? So here is the conjecture. The function that's written here satisfies this inequality for all symmetric convex sets, where this function is given as basically, it's given interval to interval. So we have a collection of intervals ek, and on each interval, the function is some dilation and shift of the function that I call Rk of A, where Rk of A is the radius of the K round cylinder of Gaussian measure A. So what do I mean by the radius of the k-round cylinder. Here's a frame where it's written explicitly, but on the picture, if we have a k-round cylinder, so I remind you it's a ball, b2k times r b2k times some space. So it's just the radius of that ball. That's the distance from the origin to the boundary of that k-round cylinder. And rk of a is so it's a k-round cylinder of measure a. It corresponds to k-round cylinder of measure a. You can, of course, write it down explicitly in terms of special functions, as written here in the last box. Maybe it's not so important for the talk. I want to say that this is natural because this RK of A is also like a metric quantity of the isoperimetric minimizer. Remember, in the case of Ehrhard inequality, phi inverse is a function that appears in the Ehrhard inequality, and it corresponds to the metric property of the subspace, and t to the power n is a function in the Minkowski case, and it corresponds to the radius of the ball. So this is somewhat natural. Funny enough, it took me actually some time to realize that this is the form of this conjecture. So initially, I realized that there is this is the explicit form of the conjecture. You can write it down. I'll not spend time explaining why, but this form is explicit in the sense that here at least the intervals are specified. The C2 function. Again, it doesn't matter so much. Probably it's easier to remember it in the form as the function that interval per interval equals to the radius of the corresponding k-round cylinder. So I conjecture that this function does give the Ehrhard type inequality for symmetric convex set. So how does this question relate to other questions? Unfortunately, I can't say that it relates a lot. One thing that one can say, at least, that if this conjecture was true, then it would give the result of Borchesi-Julien, which is the symmetric Gaussian isoperimetry, on a very small interval close to 1. So one would be able to show, if that conjecture was to hold, then one would be able to show that for sets of large measures, the strip is indeed the isoperimetric minimizer. It's not super exciting because we don't know if this conjecture holds, and we do know that the result of Borchesi-Julien is true, but still it's reassuring somewhat. So the proof sketch I'm not going to focus on. It's very similar to the proof of Ehrhard inequality. Unfortunately, one cannot do such a thing in general because we cannot let. So in the case of Ehrhard inequality, we were letting that little balls that we were reading to go to infinity. Here we cannot add this parameter and let it go up because we actually don't expect equality cases to hold for, let's say, any two round cylinders. The equality cases would only be round cylinders if they're near each other in the measure. There's some serious issue. I do think that hopefully maybe there is some way to deduce it though, but differently via local form somehow. Unfortunately, I don't know how. So the question is, I don't know if the symmetric Ehrhard conjecture would imply the Gaussian symmetric isoperimetry in the entire control. So that's one thing. Now, another very nice inequality about the Gaussian measure in symmetric convex sets is this S inequality of Galyna Livshyts, who says that if we have any symmetric convex, for example, formulation is like this: if we have any symmetric convex set K with fixed Gaussian measure, then for any t bigger than 1, the measure of the dilation of K is bigger than the measure of the dilation of the strip, where that strip has the same measure as K. So again, if that symmetric Ehrhard conjecture holds, then for an interval close to 1, one could deduce that S inequality. So this is, again, perhaps not so exciting because S inequality we do know, and here it's a conditional statement only on some small interval. However, of course, I don't know, it's again pretty encouraging. Something remarkable about this S inequality is that the proof that was given by Natalia Shkevich, it requires actually, in fact, heavy computations and almost some computer-assisted approach a little bit to some extent. So it would be interesting to see other ways. I'd like to also remark that the symmetric Ehrhard inequality, if we assume that it holds, and if we assume that the Gaussian isoperimetry holds, we don't know if it holds or not, then one could actually get that, but at least on the plane, the following curious property holds for any convex set, symmetric convex set of measure between 0.5 and 0.6, roughly speaking. the average of the mean curvature of the trace of the second fundamental form on the boundary with respect to the Gaussian measure would be maximized on a ball. It's kind of curious. I don't know if it's true or false. Maybe it's actually false, and that way one could show that both of these conjectures cannot hold at the same time. Or maybe one can show that it's always true. I don't know. Again, it's a curious question. I don't know. Are there any questions so far? Finally, I need to get to the place where I tell you something that I do know, right? Because I don't know things that I don't know. Now, here's another question that's in a couple of slides I explained is not at all different. And it's maybe, I'm mentioning it in this form because it's just the easiest way for me to explain my results. But in any case, so suppose we have a log concave measure mu, even, and suppose we have a pair of symmetric convex sets K and L of measure at least A. So both K and L have large measure, bigger than A. Consider the parameter P as mu A to be the largest exponent that we can put in this Minkowski type inequality with mu here. This is something that we heard in the Rand's talk already. Not in this form, but we heard something of that sort, right? And additionally, one can consider for any convex set K a local version of the parameter, something that holds for any set L with that set K, locally for lambda very close to 1. Okay, one can see by log concavity actually that if we were able to, so the question of the slide is how to estimate this parameter from below. What optimal power can we put in such an inequality? And one can see that if we want to know the optimal value of the function P as mu A, then we could just find a global estimate for every convex set K, because it's just given by the infimum of this P as mu of a convex set. 3 seconds of history here. So we heard a little bit of it in the Rand's talk also. So Galyna and Livshyts conjectured that for the Gaussian measures, this power is uniformly bounded by 1 over n everywhere. Later, people believed, I believe that we wrote it in this paper with Constantine for the first time, that any even log concave measure should satisfy it with respect to symmetric convex sets. Together with Mastiglieti and Livshyts, we showed that this conjecture would follow for any log concave measure if the log Minkowski conjecture was true. That's celebrated. We will hopefully hear about it more in some upcoming talks. We haven't heard yet. So in this paper with Constantine and Mastiglieti, we verified it's sort of close to a ball. If the set is very close to a ball, and in general, in this paper, we kind of initiated the study of this Galyna-Livshyts conjecture as well as the log Minkowski conjecture via the local versions. For instance, we derived also the local version of the log Minkowski conjecture, and of course later there was a lot of very important follow-up, in particular by Kolesnikov and Milman. But this is where we really started the study of that Galyna-Livshyts conjecture and log Minkowski conjecture locally. So later, together with Sasha Kolesnikov, we showed that this exponent is bigger than 1 over 2n. In fact, it's true not just for symmetric convex sets, but for sets containing the origin, curiously. And later, there was a very beautiful paper of Ashkenazis and Mashkidis where they showed that 1 over n, the optimal exponent, can be put here. So they followed our scheme and they found this very beautiful trick. And later also, Skin and Rotem, as we heard in Rand's talk, showed the same for all rotation invariant measures, which is quite remarkable. Log concave here. I showed again some general bound for this measure for all log concave measures. Instead of 1 over n, we can put n to the power minus 4. Another thing, however, I wanted to notice that just taking lower bounds on the power actually doesn't tell you that much information, because from Ehrhard inequality, for instance, we can see that this power for very large set, if the measure tends to 1, the power tends to infinity. So talking about bounded from below by 1 over n is not much if it actually tends to infinity, and we actually know that. So it maybe is more meaningful to talk about the optimal functions that would work for sets of all measures in an optimal way. And so I want to now explain that, of course, the symmetric Ehrhard conjecture that I mentioned earlier with this function is true if and only if this concavity power, whatever you want to call it, for the Gaussian measure is minimized on the k-round cylinder. So the optimal body for that local power to be the smallest is always one of the k-round cylinders. So depending on the value of A, it's a different guy every time. So whichever the smallest is the minimized. So it's equivalent conjecture. So basically, long story short, everything is about bounded from below this PS gamma somehow. And I'm about to explain some bounds that I was able to obtain for it. Before I explain you that bound, let me tell you a little bit about energy minimization. So we know from Olli's talk already yesterday about torsional rigidity, right? So torsional rigidity is defined as here. It's a supremum over all functions of the zero on the boundary of the integral of this pair of integrals. It's I define it with also normalization constant here. It's not exactly a good way I did it, but it's not maybe a good idea. In our paper, it was only different. In any case, it's not very important. So here I put index f here for some function, Lipschitz function f. And one can show it's unbelievably classical, and everybody knows that the supremum is equal to the infimum of the energy of this equation. And the equality is attained if and only if the function is zero on the boundary. And by the way, in my paper, one of the things I obtained stability version for that result in some sense. If the energy is close to, it probably is known. I don't know, but in any case, if the energy is close to the minimal of that equation, then the variance of the function of the boundary is not very large. That was one of the things that were needed for the result. So I was able to show that this concavity power is bounded from below by double the torsional rigidity of k minus the variance of the function f plus this additional factor. So here f could be taken arbitrary Lipschitz function, whose integral is 1. And moreover, the equality in that estimate is attained if and only if k is a k-round cylinder or some radius. So the key part of the theorem I want to emphasize is exactly this equality case characterization. The heart, it involves some technical details at the very least. So, but it's encouraging that one can indeed estimate from below this concavity power and really see this k-round cylinders appear as equality case. So they appeared naturally. It's not artificial here. So I don't have any time. I wanted to say that as a corollary, of course, one can, in principle, pick specific function and get something more nice rather than some abstract torsional rigidity. One can get explicit quadratic form of some stuff. One can explicitly compute it for cylinders. Along the way, I obtained the equality case characterization for this version of the Brascamp-Leib inequality, which, by the way, was not known. It was known in the Gaussian case, was due to Figali Filipis, as well as Beck and Jerison, as well as Patti and Courtade, but it was not known in general. So I wanted to just say one word, why round cylinders. So the cylindriness comes from that equality case characterization in the Brascamp-Leib inequality, whereas the roundness comes from the fact that torsional rigidity really is saturated on quadratic functions, which are constant on the boundary. And if a quadratic function is constant on the boundary, you have a round cylinder. So thanks for your
Thanks, Galyna.